Welcome back, everyone. We're continuing our math deep dives, and today we're taking a look at Zeckendorf's theorem.
Yeah, it's a pretty neat concept that shows how there's an order to numbers, even when they seem kind of random at first glance.
Right. Now, before we get into the details, let's quickly remind everyone what Fibonacci numbers are.
Sure thing. So the Fibonacci sequence is a set of numbers, starts with 1, 1, and then each number after that is the sum of the two numbers before it.
Like 1 plus 1 equals 2, then 1 plus 2 equals 3, then 2 plus 3 equals 5, and so on.
Exactly. So you get the sequence 1, 1, 2, 3, 5, 8, 13, and it keeps going forever.
Okay. Now, where does Zeckendorf's theorem fit into this?
Well, Zeckendorf's theorem says that you can represent any positive whole number as a sum of Fibonacci numbers, but there's a catch.
What's that?
You can only use Fibonacci numbers that are not next to each other in the sequence. No consecutive Fibonacci numbers.
Okay. Can you give us an example?
Let's say you have the number 64. You can write it as 55 plus 8 plus 1.
Ah, okay, I see. All those are Fibonacci numbers.
Right, and none of them are consecutive in the sequence. This is the unique Zeckendorf representation of 64.
Wait, so you're saying there's only one way to do this for any number? I mean, surely there are other ways to add up Fibonacci numbers to get 64, right?
Yeah, you're right. There might be other ways to get 64 using Fibonacci numbers, but only one way follows Zeckendorf's rule about no consecutive numbers.
So how do we find this unique representation for any number we're given? It sounds like it could get pretty complex.
It's actually simpler than you might think. We use something called a greedy algorithm.
Greedy algorithm. I've heard that term before, but I'm not quite sure I remember what it is. Can you explain it?
A greedy algorithm is a way of solving a problem where at each step you make the best choice you can right then without worrying about the long-term consequences.
Okay, so in this case, how would that apply to Zeckendorf's theorem?
So for 64, we'd start by choosing the biggest Fibonacci number that's smaller than 64.
Which would be 55.
Correct. Then we subtract 55 from 64, and we're left with 9. And we do the same thing again. The largest Fibonacci number smaller than 9 is 8.
Okay, so we subtract 8 from 9, leaving us with 1, which is also a Fibonacci number. And that's it, right? 55 plus 8 plus 1 gives us the unique Zeckendorf representation for 64.
Exactly. That's the greedy algorithm in action, always grabbing the biggest possible Fibonacci number.
That's pretty clever.
Yeah.
Now, earlier you mentioned something about the history of this theorem and Stigler's law of eponymy, which sounds kind of intriguing.
Yeah. So Stigler's law is this kind of funny idea in science. It says that discoveries are usually not named after the person who actually discovered them. And Zeckendorf's theorem is a good example.
Really? So who was the actual discoverer?
A Dutch mathematician named Lekkerkerker published the same theorem about 20 years before Zeckendorf did.
Wow, so Zeckendorf's theorem wasn't actually discovered by Zeckendorf?
Nope. It happens more often than you might think in science. It's a funny quirk of history.
Interesting. So we know every number has a Zeckendorf representation. But how do we know it's really unique? It seems like it would be tough to prove that.
Well, it does involve some math, but the main part of the proof depends on a lemma. A lemma is like a mini theorem that helps you prove a bigger one. This particular lemma says that if you add up any bunch of non-consecutive Fibonacci numbers, the sum will always be smaller than the next Fibonacci number in the sequence.
Let me make sure I understand this correctly. So if we take, say, 2, 5, and 13 from the Fibonacci sequence, their sum will always be less than 21, which is the next Fibonacci number after 13.
Yes, precisely. And this lemma helps prove that the Zeckendorf representation is unique. It means there can't be two different Zeckendorf representations for the same number.
It's like a mathematical jigsaw puzzle then.
Yeah.
Only one way to put the pieces together to get the complete picture.
That's a great way to put it.
Now, we've been talking about how to find the Zeckendorf representation, but I'm also curious about why this pattern exists. What's so special about Fibonacci numbers that makes this work?
That's a great question, and it takes us a bit deeper into why math is so cool. The Fibonacci sequence has all sorts of amazing properties. Like as you go further along the sequence, the ratio between consecutive Fibonacci numbers gets closer and closer to a special number called the golden ratio.
Ah, the golden ratio. I've heard of it, but could you remind us what it is?
The golden ratio, often represented by the Greek letter phi, is about 1.618. It's this irrational number that pops up in math, art, architecture, and even nature. People often associate it with things that look really balanced and pleasing to the eye.
So is there a connection between the golden ratio and Zeckendorf's theorem?
It's possible. The golden ratio is all about creating harmony and balance, and Zeckendorf's theorem, in a way, could be seen as showing this harmony in numbers.
That's a beautiful way to think about it, mathematical harmony. We talked a bit about how Zeckendorf's theorem could be used in things like coding theory. Can you give us more details about that?
Sure. Imagine you want to create a secret code. You could use Zeckendorf representations to hide your messages. Each number in your message could be swapped for its unique Fibonacci combination.
So instead of saying the actual number, you'd send its Zeckendorf representation.
Exactly. If someone doesn't know about Zeckendorf's theorem, the message would look like a random bunch of Fibonacci numbers.
That's clever. What other fields could benefit from this theorem?
Computer science is another area, specifically in storing and retrieving data. Imagine you have a huge amount of data you need to store efficiently. Instead of storing the actual numbers, you could store their Zeckendorf representations.
And that would be more efficient.
In some cases, yes. Remember, each Zeckendorf representation is unique and uses those non-consecutive Fibonacci numbers. This could help compress the data and make it easier to find and fix errors.
So something that seems abstract at first could actually be quite helpful in technology.
Exactly. It shows how math, even the stuff that seems purely theoretical, can have real-world uses we might not expect.
Earlier, we briefly mentioned Fibonacci numbers, which sounds pretty wild. Can you tell us more about those and how they relate to Zeckendorf's theorem?
Definitely. Just like we can keep going forward with the Fibonacci sequence to get bigger and bigger numbers, we can also go backward into negative numbers. These are the Fibonacci numbers.
So if the Fibonacci sequence starts with 1, 1, 2, 3, 5, 8, and so on, what would the Fibonacci sequence look like?
It would go in the other direction, still following the same rule of adding the previous two numbers. So you'd get -8, 5, -3, 2, -1, 0, 1, 1, 2, 3, 5, 8, and so on. See how the signs alternate.
That's pretty good. So do these Fibonacci numbers also have something to do with Zeckendorf's theorem?
They do. Just like any positive whole number can be uniquely represented using non-consecutive Fibonacci numbers, any negative whole number can be uniquely represented using non-consecutive Fibonacci numbers.
Wow, so it's like Zeckendorf's theorem has a mirror image in the world of negative numbers. That's amazing.
Yeah, it really is. For example, anaglivin can be written as the sum of megalis 8 and megath3, both of which are Fibonacci numbers.
It seems like we found hidden order not just in positive numbers, but also in negative numbers, using Fibonacci and Fibonacci numbers. Makes you wonder what other patterns we haven't discovered yet.
It really does. Math is full of surprises.
Yeah, it really makes you appreciate just how elegant and deep math can be. Who knew just adding numbers could lead to such incredible discoveries?
It really shows you the power of thinking mathematically. A lot of the most beautiful patterns are kind of hidden, just waiting for us to find them.
And Zeckendorf's theorem seems like just the beginning. We've seen how it works with positive numbers, negative numbers, and might even be useful in things like coding and computer science. Makes you wonder what other crazy patterns are out there.
It's exciting to think about, right? Maybe there are Zeckendorf-like things in science or art, or even how people behave. What if we could represent emotions or ideas or historical events using some kind of unique combination, like Zeckendorf's theorem? That'd be a whole new way to understand the world around us.
Whoa, that's a really cool thought. It shows how math can give us completely new ways to see and understand things, even stuff beyond just numbers.
Absolutely. It also shows how everything is connected. Sometimes the biggest breakthroughs come from finding links between things that seem totally different at first.
So before we go too far down that rabbit hole, let's bring it back to Fibonacci numbers for a second. You mentioned them earlier, and they sound pretty mind-blowing. Can you tell us more about what they are and how they relate to Zeckendorf's theorem?
Sure. So we know we can keep going forward with the Fibonacci sequence and get larger and larger numbers, right? Well, we can also go backwards into the negative numbers. Those are the Fibonacci numbers.
So if the Fibonacci sequence starts with 1, 1, 2, 3, 5, 8, and so on, what does the Fibonacci sequence look like?
It goes the other way, but still follows the same rule, adding the previous two numbers. So it goes -8, 5, -3, 2, -1, 1, 0, 1, 0, 1, 2, 3, 5, 8, and keeps going. Notice how the signs switch back and forth.
Oh, yeah, that is interesting. So do these Fibonacci numbers also fit in with Zeckendorf's theorem?
Turns out they do. Just like we can write any positive whole number as a unique sum of non-consecutive Fibonacci numbers, we can write any negative whole number as a unique sum of non-consecutive Fibonacci numbers.
Wow, so it's like Zeckendorf's theorem has a twin in the negative number world. That's amazing.
It is pretty wild. For example, you can express -11 as the sum of -8 and -3, both negative Fibonacci numbers.
It seems like we found a hidden order, not just in positive numbers, but also in negative numbers, using Fibonacci and negative Fibonacci numbers. It makes you wonder what other patterns we haven't discovered yet.
Right. Math is full of surprises.
It really is. It just shows how powerful math is. And Zeckendorf's theorem, it's a great example of how there's always more to learn, even in things we think we know.
I totally agree. And who knows what other cool theorems and patterns are waiting for us to find them.
Well, on that note, we encourage all our listeners to keep exploring and asking questions, keep digging deeper into the world around us. Until next time.